Now start lemmas in basis for topology. First we discuss first lemma, which one is the topology equal to union of some basis element. Next we now going to second lemma. We first write the statement of lemma. The statement of lemma is let X be a topological space let or suppose that C is a collection of open sets of X. Suppose that C be the script C be the collection of all open subset. Collection of open sets of X. Such that for each open set U of X, such that for each open set U of X, and each X in U, there is an element C in script C such that X belongs to C subset of this U, then script C, the collection, is a basis for the topology of X. Now prove it. X topological space C with the collection of all open sets of X such that for each open set U of X and each X belongs to U, there is an element C from this collection such that X belongs to this C subset of this U open set, then C is a basis for the topology of X. We prove it now. We must prove C is a basis first. Then we prove, we have to show C is a basis. Basis, then two criteria. First criteria X belongs to X. There exists C belongs to script C such that X belongs to C. Second criteria, X belongs to C1 intersection C2, then there exists a C3 belongs to script C such that X belongs to C3 subset of C1 intersection C2. Here all C are open, so X belongs to C subset of X we find. Okay, X belongs to X implies there exists C belongs to script C such that X belongs to C subset of X we find. Because by open set and definition of open set, X also open and C also collection of open sets, so we find this. And also C1 C2 are open and this contain X, then C1 intersection C2 also open. C1 open, C2 open, then C1 intersection C2 is also open, because if X belongs to some B delta X, subset of C1, X belongs to some B delta 1 X, subset of C2, then X must be belongs to B of minimum delta of delta 1 X, subset of C1 intersection C2. Okay, so X belongs to this one. Then we construct, this one is hold, then we construct now tau the collection of open sets of X, tau the collection of open sets of X, let tau be the collection, let tau be the collection of all open sets, tau be the collection of all open sets of X, we must show that we must show that the topology tau dash generated by C equals the topology tau. We must show that tau dash generated by C must equal to tau. First we considered, let U belongs to tau. Some open set U belongs to tau. If X belongs to U, by hypothesis X belongs to C subset of U, it follows that U belongs to the topology tau dash. It follows that X belongs to tau dash, because X belongs to C and C is the open set which generate tau dash one topology, so X belongs to tau dash. Okay, this implies that U belongs to tau dash. U belongs to tau, X belongs to U, X belongs to C by condition. Then obviously here C, as C belongs to tau dash, so U belongs to tau dash. Okay, hence tau subset of tau dash. Now let W belongs to tau dash. W belongs to tau dash means W equals a union of elements of script C. W equals union of elements of script C. Since each element script C belongs to tau, since each element of script C is open and belongs to tau, so W belongs to tau. Since tau is topology, and each element of C is open and belongs to tau, so W belongs to tau since tau is topology. So we find tau dash subset of tau. This implies that tau dash equal to tau. Okay, then we prove this lemma, whose lemma X is topological space and C is the collection of open sets of X such that for each open set U of X and each X in U, there is an element C of script C such that X belongs to C subset of U, then script C is a basis for the topology of X. That means some collection of open sets from a basis of topology of X. Okay, some collection of open sets from a basis for a topology of X. Now we proceed this important lemma. This important one, compare to topology by some property. Compare to topology some property. How we compare? We write the statement of lemma. Lemma said that beta, script beta and script beta dash be bases for the topology tau and tau dash. Let script beta and beta dash be the basis for the topology tau and tau dash respectively on X. Then we compare between tau and tau dash. That means first one, tau dash is finer than tau, and second one is for each x belongs to x, each basis element B belongs to script B containing X. There is a basis element beta dash belongs to script beta dash such that X belongs to script beta dash subset of B beta. That means if tau dash is finer than tau, then basis element of tau dash must be subset of basis element of tau. Okay, and that means any one element of X which contain some basis element of tau must be contain one basis element of tau dash. Okay, now we proceed to prove. Proof is very simple and easy. First we prove, that means we assume two are hold and then we proceed one. That means we prove one. Given an element U belongs to tau, U is open, we wish to show that U belongs to tau dash. Then tau dash must be finer. That means tau dash is superset of tau. Okay, or tau subset of tau dash. Now let X belongs to U. Then beta generates tau. That means there is an element, there is this b belongs to script beta, b belongs to script beta such that x belongs to b subset of u. Now there is an element beta dash belong to script beta dash such that x belongs to beta dash subset of beta by condition 2 subset of u. This one is by condition 2. Then we find x belongs to beta dash subset of u. So we find that u belongs to, we implies that u belongs to tau dash. This implies tau subset of tau dash, or tau dash is finer than tau. Now we prove second one, that means 1 implies 2. 1 implies 2. How it can be done? This one also so simple. We use the condition tau dash is finer than tau. Then we proceed to prove there exists x belongs to x, each basis element b contain x. We find a basis element b dash belongs to script b dash such that b dash contain x also, and obviously b dash is subset of b. How we prove it? First, 1 implies 2. How we prove? Let x belongs to x, then b belong to script b, x belongs to b. Obviously, because by definition of basis, okay, this one is done. Then b belongs to tau, okay, and also tau subset of tau dash, that means tau dash is finer than tau. This one is the condition. So b belongs to tau dash also, and obviously beta belongs to script beta dash, and beta dash is basis for tau dash. Then we find some beta dash, x belongs to beta dash subset of b. Okay, since tau dash generate and b belongs to this one, this implies that x belongs to beta dash subset of b. Okay, because tau dash is generated by b dash, script b dash. So we find this one is the second condition of the lemma. That means we prove this lemma. So quickly we prove it, and this lemma is very important to us because we compare this to topology on some set x. This two topology is tau and tau dash, and here script b, here script b dash be the basis. Then we find if tau dash is finer than tau, then x belongs to b. We find the x is beta dash belong to script beta dash, x belongs to beta dash subset of b. Okay, now we proceed further. Some example. This example is too easy. Same thing, circular region and same topology as beta dash of redirect. That means we construct this one is circular region of a plane. and beta dash rectangular region of a plane, then we see that some point x belongs to some circular region, obviously belongs to some rectangular region. Obviously some point in some rectangular region must belongs to one circular region. Okay, so here beta and beta dash are both compare with each other or comparable with each other. That means here we find tau, if this one generate topology tau and this one generate topology tau dash, then both are same topology. Okay, then what we find? We find both are same topology, because from this we find tau subset of tau. This one is find tau subset of tau dash subset of tau. Here we find tau subset of tau dash. That means tau is tau dash is finer than tau. Here tau is finer than tau dash, so it implies tau equal to tau dash. Okay, then these two are generate same topology, so their basis of a topology class 2 is end.